There's a reason your Power BI dashboards refresh just fine while your production line stutters. The same cloud that makes your reports instant makes your robots unstable. And the fix isn't faster internet. It's a complete architectural inversion that most cloud teams haven't considered yet. The physics you can't cheat. Your cloud strategy was built on an assumption that worked beautifully for knowledge work. The assumption is that a few seconds of delay doesn't matter. A report that refreshes in a minute feels instant to the human reading it. A chatbot that responds in under a second feels instant. A workflow that completes in 10 seconds feels instant. Even a dashboard that takes 30 seconds to load is tolerated because the human brain is busy doing other things while it waits. But that assumption breaks the moment you connect physical machinery to digital systems. And in 2026, nearly every industrial organization is doing exactly that. A robotic arm performing a pick-and-place operation on a fast-moving conveyor doesn't have seconds. It has milliseconds. The arm must receive sensor data, process it, adjust its trajectory, and issue motor commands in a loop that repeats every 1 to 10 milliseconds. If the loop slows down, the arm misses the target. If the loop speeds up unpredictably, the arm overshoots. Jitter, which is the variability in latency from one loop to the next, is often more dangerous than consistently slow latency because control systems are tuned for predictable timing. A computer vision camera inspecting parts for defects doesn't have minutes. It has fractions of a second to flag a problem before the faulty part advances down the line, gets welded into a chassis, or packaged into a box that a customer will open. The cost of a missed defect isn't just the scrap cost of one part. It's the warranty claim, the recall, the brand damage, and the regulatory fine. An autonomous guided vehicle navigating a warehouse aisle doesn't have the luxury of waiting for a response from a cloud region 500 kilometers away. The vehicle is moving, the people around it are moving, the other vehicles are moving. A 300 millisecond delay between seeing an obstacle and deciding to stop is the difference between a near miss and a collision. The problem isn't that your cloud is slow. The problem is that physics doesn't negotiate. Light travels through fiber at roughly 200,000 kilometers per second. That sounds fast because it is fast, but it translates to about 5 microseconds of one-way delay for every kilometer of fiber between your factory and the data center. Over 1,000 kilometers, the physical minimum one-way latency is already about 5 milliseconds, which means a round trip takes at least 10 milliseconds before a single router, switch, firewall, or protocol handshake adds even 1 microsecond of overhead. In practice, real networks rarely achieve those theoretical minima. Traffic traverses multiple hops, detours through peering points, passes through encryption devices, and waits in queues. The effective round-trip latency between an industrial site and a cloud region easily reaches 30 to 80 milliseconds in well-connected geographies, and it climbs much higher in remote regions. Under congestion, the round trip can spike to hundreds of milliseconds without warning. For a Power BI dashboard, 30 milliseconds is nothing. It's below the threshold of human perception. For a robotic control loop that needs to update every 1 to 2 milliseconds, 30 milliseconds is 15 to 30 control cycles that never happened. It's slow. And worse, it's unstable. It's unsafe. Jitter makes the problem worse. Jitter is the variability in latency from one packet to the next. A network might average 30 milliseconds, which sounds manageable until you realize that some packets arrive in 10 milliseconds and others arrive in 200 milliseconds. A control system tuned for predictable timing can't handle that variability. It overcorrects, then undercorrects, then overcorrects again. The result is oscillation, mechanical wear, and in the worst cases, collision or injury. Determinism, which is the consistency and predictability of response times, matters more than raw speed. A system that responds in 5 milliseconds every single time is more valuable than a system that averages 3 milliseconds but occasionally spikes to 300. Protocol overhead adds another layer that cloud architects often overlook. Every packet traversing a wide area network passes through firewalls, load balancers, encryption tunnels, and protocol handshakes. Each of these elements adds a small delay, a few microseconds for encryption, a few milliseconds for firewall inspection, a few more for border gateway protocol convergence. In isolation, none of these overheads are large, but they are additive and they are variable. A firewall under load might queue packets for 10 milliseconds. A virtual private network tunnel might renegotiate its session, adding 100 milliseconds of delay. These aren't bugs, they're normal behaviors in a shared network. But normal behavior for a web application is catastrophic behavior for a control loop. And here's where the architectural mistake happens. Most cloud strategies were designed in a world where centralization delivered clear economies of scale and operational simplicity. Data lakes were built in a few large regions. Identity and security policies were centralized. Connectivity patterns assumed that branch locations and factories were essentially spokes feeding into a hub. This model works extraordinarily well for transactional systems, collaboration, and offline analytics. It breaks when the edge becomes a locus of real-time decision-making. The hub-and-spoke model assumes that the edge consumes intelligence from the center. The factory requests instructions, the cloud responds, the factory executes. That pattern is fine for batch production schedules, inventory reports, and quality summaries. It's catastrophic for closed-loop control, safety interlocks, and real-time collision avoidance. In those scenarios, the edge doesn't need instructions from the center. The edge needs to be the center of its own local universe. When milliseconds matter, smart manufacturing provides some of the clearest examples of where the latency wall manifests, but it's not the only sector hitting the wall. The same physics applies in logistics, healthcare, energy, mining, ports, and agriculture. Modern factories deploy fleets of industrial robots, automated guided vehicles, collaborative robots, and computer numerical control machines. These devices depend on precise timing and coordination that most information technology professionals never encounter in their day-to-day work. A robot aligning itself with a moving target on a conveyor may need sensor readings and motion commands at intervals of 1 to 10 milliseconds. If the control loop that aligns the robot runs over a wide area network to a distant cloud region, the variability in latency creates a dangerous oscillation. The robot overshoots, corrects, overshoots again. Even if the average latency looks acceptable in lab conditions, occasional spikes or congestion events create hazardous conditions that simply don't exist when the control logic runs locally. Real-time computer vision is another workload that stresses traditional cloud strategies. A single high-definition video stream at 30 frames per second generates several megabits per second of raw data. A factory with 50 cameras is pushing hundreds of megabits per second. A logistics hub with 200 cameras is pushing gigabits. Streaming all of that footage to a cloud region for analysis is often cost-prohibitive. But the bandwidth problem is only half the story. If the inspection must happen in real time, so the system can reject a faulty item before it leaves the conveyor or halt a machine when a human body enters a hazardous area, then the latency budget shrinks to tens of milliseconds. Sending each frame to a cloud region for inference and waiting for the result is usually impractical. Even if the average latency is low enough, variability in network conditions yields occasional slow responses that are unacceptable when safety or quality is at stake. A vision system that catches 99% of defects but misses 1% because of network jitter isn't a quality system, it's a liability. Autonomous vehicles in industrial settings face a similar wall. An autonomous guided vehicle in a warehouse depends on dense sensor fusion and control algorithms to navigate safely among people, equipment, and other vehicles. For collision avoidance and immediate maneuvering decisions, the vehicle must rely on local sensing and processing because delays of even a few hundred milliseconds can be unsafe. A cloud-only architecture that offloads too much of the autonomy stack to a distant region is worse than inefficient. It's a safety risk that your insurance underwriter, your safety regulator, and your operational technology team will reject. Healthcare environments add another dimension. Real-time telemetry from patient monitors, infusion pumps, and imaging devices is clinically important, and the data is highly sensitive. Many jurisdictions impose strict constraints on where health data can be stored and processed. A cloud-only approach where critical telemetry depends on a distant region fails both the latency test and the sovereignty test. In a telemetry system where a few seconds of delay might miss a cardiac event, centralization isn't a feature. It's a patient safety issue. Energy grids and critical infrastructure operate under some of the strictest reliability requirements of any sector. Grid protection systems often react in sub-cycle timescales to faults and disturbances. These functions will never move to the cloud. They belong close to the equipment and follow deterministic, hard real-time design principles. When utilities try to centralize too much operational control in shared information technology networks or cloud environments, they create dependencies that might fail during storms, cyber incidents, or other disruptions. The consequences of a failed protective relay aren't measured in downtime dollars. They're measured in blackouts. Mining operations illustrate the problem at geographic scale. A surface mine might span tens of square kilometers. The pit is deep, the haul trucks are massive, and the network connecting the pit to the nearest town, let alone the nearest cloud region, is often microwave or satellite. Autonomous haul trucks operating in these environments can't depend on a cloud control loop. They must make pathfinding, collision avoidance, and loading decisions locally. The latency wall isn't an abstract concept in a mine, it's a physical reality created by distance, terrain, and weather. Ports and maritime logistics present similar challenges. A container terminal might stretch across several kilometers of quay, yard, and gate. Automated stacking cranes, automated guided vehicles, and ship-to-shore cranes must coordinate in real time across a radio footprint that Wi-Fi can't cover reliably. Private 5G networks in ports aren't a technology upgrade. They're a coverage necessity. Smart buildings and retail operations illustrate the latency wall in less dramatic but equally costly ways. An automated checkout system that depends on cloud-based facial recognition or item detection can't afford multi-second variability. A customer who waits 5 seconds for the register to authorize a purchase will abandon the cart. A dynamic pricing display that depends on cloud inventory lookups will show stale prices during a flash sale, creating customer complaints and revenue loss. These aren't safety-critical scenarios, but they are revenue-critical scenarios where the latency wall manifests as customer friction rather than mechanical failure. The common thread across all these scenarios isn't that the cloud is bad. The cloud is extraordinary for analytics, planning, optimization, and monitoring tasks that tolerate seconds or minutes of delay. The thread is that a purely centralized strategy is insufficient for industries where milliseconds matter and where regulatory and physical constraints dominate. The old model versus the new model. Most organizations built their cloud strategies around a set of assumptions that made perfect sense at the time. Centralize data in a few hyperscale regions, consolidate workloads into shared platforms, rely on global connectivity to bridge the last mile. These assumptions created enormous value for knowledge work, business intelligence, and enterprise collaboration. They simplified procurement, reduced vendor management overhead, and allowed central teams to enforce standards. But those same assumptions create a structural mismatch when the edge becomes a source of real-time decisions. In the old model, the factory floor was a consumer of central services. Data flowed from machines to the cloud. Commands flowed from the cloud back down. The cloud was the brain. The edge was the body. This model worked because the edge didn't need to think. It just needed to report and execute. In the new model, the edge is also a brain. The factory floor makes local decisions in real time. It filters raw data into insights before anything leaves the building. It continues operating even when the wide area connection drops. The cloud doesn't disappear. It shifts from being the primary control plane to being the training ground, the governance layer, and the long-term analytics engine. This isn't a rejection of the cloud. It's a rebalancing. It's a recognition that different workloads belong at different layers of the edge-to-cloud continuum. The old model treats latency as a networking problem that can be optimized away with better bandwidth, content delivery networks, or WAN acceleration. Engineers are trained to believe that if the link is slow, you add more bandwidth. If the route is long, you deploy a content delivery node. If the protocol is inefficient, you tune it. These are good instincts for web applications and file transfers. They are irrelevant for control loops. The new model recognizes that latency is a physics problem with a hard floor. The speed of light and fiber is a constant. The distance between your factory and the cloud region is a constant. The number of routing hops is a variable, but not one you can reduce below a physical minimum. The only way to beat the latency wall is to move the compute closer to the workload. The old model assumes that more virtual CPUs in the cloud or a faster storage tier will improve end-to-end behavior. If the database is slow, provision a bigger instance. If the query is slow, add an index. These instincts are correct for transaction processing and analytics. They are wrong for control loops. Once you hit the latency wall, adding more cloud capacity does almost nothing to improve actual response times for millisecond scale tasks because the bottleneck is the network path, not the compute path. The old model backhauls massive volumes of raw sensor and video data because the cloud is where the analytics tools live. The data science team needs the raw data. The machine learning pipeline needs the raw data. The compliance auditor needs the raw data. So every byte gets shipped upstream. The new model processes and filters that data at the edge, sending only metadata, anomalies, and aggregates upstream, which dramatically reduces backhaul costs and bandwidth requirements. The data science team still gets what they need. They just get it in a refined form that travels faster and costs less. The old model assumes connectivity is always available. The wide area network is reliable. The internet service provider is reliable. The cloud region is reliable. The new model designs for brownouts and outages, ensuring that critical operations continue even when the WAN is impaired. This isn't pessimism, it's engineering. If your emergency shutdown system depends on a cloud connection, what happens when the fiber backhaul cuts the line? The shift from old model to new model isn't a software update, it's an architectural inversion. And most cloud teams haven't been trained to think this way because their entire career has been built around centralization. Their certifications, their playbooks, their vendor relationships, and their mental models all assume that the cloud is the right place for compute. They need to unlearn that assumption for a specific class of workloads. This unlearning is harder than it sounds. Cloud architects are rewarded for consolidation. Fewer regions means simpler governance. Fewer vendors means simpler procurement. Centralized logging means simpler compliance. These are good instincts, but they become dangerous when applied indiscriminately to workloads that require physical proximity. The new model doesn't ask you to abandon centralization. It asks you to recognize that centralization has a domain of applicability, and that domain ends where the latency wall begins. The organizational resistance to this inversion often manifests as a debate about cost. A cloud engineer sees the per-hour cost of an Azure Stack Edge appliance and compares it to the per-hour cost of a cloud virtual machine. The cloud virtual machine looks cheaper, but this comparison ignores the cost of bandwidth, the cost of downtime, the cost of scrap, the cost of regulatory fines, and the cost of safety incidents. When the full cost of the old model is calculated, including the risks it externalizes, the new model is often the cheaper option by a wide margin. The problem is that the old model's costs are hidden in operational budgets, insurance premiums, and risk registers, while the new model's costs are visible in a capital expenditure line item. Finance teams need to be educated about the total cost of ownership, not just the invoice from the cloud provider. The cost of backhauling everything. The latency wall isn't the only force pushing enterprises toward the edge. There's a financial wall. And for many organizations, it's the one that actually gets leadership's attention. A single high-definition camera at 30 frames per second generates several megabits per second of data. A factory with 50 cameras is pushing hundreds of megabits per second of raw video. A logistics hub with 200 cameras is pushing gigabits. Streaming all of that footage to a cloud region for analysis is often cost prohibitive. The egress charges alone can exceed the value of the insights the cameras generate. If you're paying cloud egress fees on 100 megabits per second of continuous video, your annual network bill can run into 6 figures before you process a single frame. Edge-based computer vision changes the economics completely. When inference runs on a local GPU or a specialized accelerator in an Azure Stack Edge appliance, the camera streams travel only a few meters over the local network. The edge node detects defects, counts objects, or flags safety violations locally. Only the results, the exceptions, and the aggregated counts travel to the cloud. The bandwidth savings are enormous, and the response times drop from hundreds of milliseconds to single-digit milliseconds. The camera that used to consume 100 megabits per second of cloud bandwidth now consumes a few kilobits per second of exception data. Beyond bandwidth, there's the cost of physical infrastructure. ABI research found that moving to private 5G in a typical factory can save hundreds of thousands of dollars per year by avoiding Ethernet cable drops. Each cable drop costs about $225 on average when you factor in cable, labor, installation, conduit, and the downtime required to rewire a production line. In a large facility with thousands of drops, the cabling budget alone can justify a wireless migration. And the savings multiply when you consider reconfiguration. In the old model, moving a machine to a new location means installing new cable runs, which means production downtime, contractor costs, and disruption. In the new model, you move the machine, update its network, slice configuration in the Azure portal, and it reconnects wirelessly in minutes. But the real cost that backhauling hides is the cost of fragility. When your production line depends on a cloud connection for real-time decisions, every one outage becomes a production stoppage. Every peering dispute between internet providers becomes a potential liability. Every cloud region brownout becomes a factory floor crisis. Every denial of service attack against your DNS provider can halt operations even though your factory itself was never targeted. The old model externalizes resilience. It assumes that the network is someone else's problem. The new model internalizes it. It designs systems that keep running when the outside world is having a bad day. Then there's the sovereignty constraint. Operational data in many industries may be subject to strict export restrictions that prevent it from leaving a facility or country in raw form. Healthcare data, defense data, energy grid telemetry, and financial transaction records often fall into this category. In the European Union, GDPR governs personal data processing at the edge, and the AI Act, reaching full enforcement in August 2026, introduces strict obligations for high-risk edge-based systems. The Data Act focuses on data ownership, access, and portability for information generated by connected products. NIS2 applies to essential and important entities across energy, transport, health, and digital infrastructure, requiring robust cybersecurity measures and incident reporting within 24 hours. Some member states demand 6 hours. Outside the European Union, the picture is equally complex. China's cybersecurity law and data security law impose strict localization requirements for critical information infrastructure operators. Russia's data localization law requires personal data of Russian citizens to be stored on servers physically located in Russia. India's draft data protection bill and existing Reserve Bank of India guidelines mandate local storage for payment system data. Brazil's general data protection law follows the European model with cross-border transfer restrictions. Vietnam's cybersecurity law requires foreign technology firms to store data locally and establish local branches. A cloud-first strategy that routes all operational data to a single hyperscale region, regardless of where that region is located, violates multiple national laws simultaneously. The financial cost of non-compliance is rising. GDPR fines can reach 4% of global annual revenue. The AI Act introduces penalty frameworks for high-risk artificial intelligence systems that fail to meet data governance and documentation requirements. NIS2 penalties vary by member state, but can include large administrative fines and liability for management. These aren't theoretical risks. They've been levied against major technology and industrial companies, and the trend is towards stricter enforcement, not looser interpretation. A cloud-first strategy that naively assumes data can flow freely to a hyperscale region violates these constraints by design. The new model keeps raw data on premises, under local control, while still leveraging the cloud for model training, governance, and cross-site analytics where permitted. It's not about avoiding the cloud, it's about controlling the data path. Together, these factors reveal that a purely centralized strategy is insufficient for industries where milliseconds matter, where bandwidth costs matter, and where regulatory constraints matter. The cloud isn't the problem. The assumption that everything should run in the cloud is the problem, but knowing the problem is only half the battle. The architecture that fixes it is already being deployed, and the return on investment numbers are going to surprise you. what private 5G actually does. Most people think 5G is about faster phones. In reality, for the enterprise, 5G is about deterministic networking. Wi-Fi is best effort. Private 5G is a guarantee. To understand why this matters, you need to understand the structural difference between the two technologies at a protocol level. Wi-Fi, even in its newest generation, uses unlicensed spectrum and contention-based access. Devices compete for airtime. When the network is lightly loaded, Wi-Fi can be very fast. When the network is crowded, when devices roam between access points, or when interference enters the environment from neighboring networks or industrial equipment, latency fluctuates unpredictably. Wi-Fi is perfect for knowledge work, office collaboration, and many non-critical Internet of Things applications. It is less ideal for deterministic, latency-sensitive industrial control because its fundamental design prioritizes throughput over predictability. Private 5G uses scheduled access. The base station, called a G-Node-B in 5G terminology, allocates time and frequency resources to each device, enforcing quality of service profiles per flow. Network slicing allows multiple logical networks to coexist on the same physical infrastructure, each with its own performance characteristics and security boundaries. One slice can carry safety-critical robot commands with sub-10 millisecond latency and bounded jitter. Another slice can carry video surveillance. Another can handle employee devices. Each slice operates independently, and the scheduling mechanism guarantees that a burst of video traffic won't delay a safety command. This determinism isn't a configuration option, it's built into the radio protocol. Ultra-reliable low-latency communication is a 3GPP service category designed to deliver latencies on the order of 1 millisecond and high reliability for critical applications. While achieving these figures in practice depends on careful design and proximity to the equipment, the architectural target is clear. Private 5G is designed for bounded, predictable performance, not peak performance under ideal conditions. The industry doesn't benchmark private 5G by asking how fast it goes on an empty channel. It benchmarks by asking how predictable it stays under load. By early 2026, the global private 5G market reached about $7.57 billion, up from $5.08 billion in 2025. Manufacturing alone accounts for 32 to 37% of that revenue, which tells you where the demand is coming from. It's not consumers downloading movies, it's industrial environments that need guaranteed connectivity for moving assets, dense sensor fields, and mission-critical control loops. The growth trajectory is steep, with analysts projecting the market to reach tens of billions by the early 2030s. Mobility is another area where 5G diverges sharply from Wi-Fi. In a large warehouse or production facility, autonomous guided vehicles and mobile robots move continuously. Wi-Fi handovers between access points can be sticky and disruptive. Devices cling to an access point too long, then drop, then reconnect. In a safety-critical scenario, that dropout is unacceptable. A robot that loses connectivity for even a few seconds while roaming might drift into an aisle, collide with a human worker, or drop its payload. 5G handovers are engineered for mobility. The device maintains session continuity as it moves between cells, with latency and jitter that stay within engineered bounds. The handover isn't an afterthought in the protocol, it's a first-class feature. Security is built into the architecture at a deeper layer than Wi-Fi. Instead of shared passwords and certificates that can be copied or leaked, private 5G uses subscriber identity modules or embedded subscriber identity modules for hardware-anchored identity. Each device has a unique, cryptographically strong identity that the network can authenticate, revoke, and monitor individually. You can't shoulder surf a SIM, you can't guess a 16-digit cryptographic key, and you can revoke a compromised device instantly without rotating a shared credential that affects every other device on the network. This isn't an add-on, it's the foundation of the access model. Spectrum is another differentiator. Private 5G networks use licensed, shared, or lightly licensed spectrum that is protected from unlicensed interference. In the United States, the Citizens Broadband Radio Service band at 3.5 GHz allows enterprises to deploy private cellular networks without acquiring traditional mobile licenses. The three-tier priority access system lets industrial users obtain priority licenses that protect their spectrum from general authorized access users. In Europe, local licensing regimes in Germany, the United Kingdom, France, and the Netherlands have enabled dozens of factory-scale private 5G deployments. Japan, South Korea, and Australia have also opened spectrum for local 5G enterprise use. This dedicated spectrum means your factory's radio environment is controlled. You're not competing with the neighbor's Wi-Fi, the coffee shop downstairs, or the handheld barcode scanner on the next aisle. The radio access network itself is a major investment, and enterprise buyers need to understand the ecosystem. The G-Node-B, which is the 5G equivalent of a cellular base station, connects to the 5G core through a front-haul or mid-haul link. Multiple vendors supply G-Node-Bs that interoperate with Azure Private 5G Core, including Nokia, Ericsson, Samsung, and several specialized industrial radio suppliers. The choice of radio vendor affects coverage, power consumption, indoor versus outdoor performance, and integration complexity. Microsoft maintains a partner ecosystem that validates specific radio combinations with Azure Stack Edge, which reduces the integration risk but doesn't eliminate it. You still need a radio engineer to plan the deployment, perform propagation modeling, and optimize antenna placement in environments full of metal, concrete, and moving equipment. Private 5G doesn't replace Wi-Fi in most facilities. The two technologies serve different layers of the stack. Wi-Fi remains the default for offices, collaboration spaces, guest access, and general enterprise connectivity. Private 5G anchors the operational technology layer, where determinism, mobility, and security are non-negotiable. The smartest architectures in 2026 are hybrid, using each technology where it wins. Around 60% of businesses see converged Wi-Fi and 5G as key to enterprise flexibility, viewing them as complementary rather than competitive. Quality of service engineering in private 5G is worth understanding because it's fundamentally different from Wi-Fi quality of service. In Wi-Fi, quality of service tags like voice priority or video priority are suggestions that access points try to honor when spectrum is available. In 5G, quality of service is a contract. The network establishes a data radio bearer with specific guaranteed bit rates, maximum bit rates, and delay budgets for each flow. If the network can't meet the contract, it rejects the bearer establishment rather than degrading performance silently. This is why 5G is called deterministic. It doesn't hope for low latency. It guarantees it or fails explicitly, which is exactly the behavior an engineer wants when designing a safety system. Azure Stack Edge and the local core. Microsoft's answer to the local compute question is Azure Stack Edge. It's a ruggedized appliance that sits on your factory floor, in your warehouse, or in your substation, and it runs Azure services locally. But Azure Stack Edge is more than a server in a closet. In the private 5G architecture, it becomes the core of your mobile network. Azure Private 5G Core is Microsoft's managed 5G core solution, and it runs on Azure Stack Edge appliances on premises. The control plane is managed through the Azure portal, which means your information technology team provisions slices, manages subscriber identities, and monitors performance using the same interfaces they already know from managing virtual machines, storage accounts, and Kubernetes clusters. But the user plane traffic, the actual data flowing between devices and applications, never leaves your facility unless you explicitly choose to send it. This distinction is critical, and it's one that many cloud professionals misunderstand at first. Cloud managed doesn't mean cloud dependent. The management plane, the orchestration layer, and the lifecycle operations live in Azure. The data plane lives on your premises. If the wide area connection drops, your local network keeps functioning. Your robots keep talking to your edge applications. Your cameras keep streaming to your local inference containers. The only thing you lose is the ability to push configuration changes or view remote dashboards until the link recovers. The factory doesn't stop because the internet hiccups. Azure Stack Edge Pro is the primary hardware platform for these deployments. It can host 1 or 2 accelerator cards to support GPU inferencing at the edge, in addition to network workloads. The network configuration supports network acceleration and specialized network functions such as packet core and software-defined wide area network customer premises equipment. This means the same appliance that runs your 5G core can also run your computer vision models, your predictive maintenance algorithms, and your digital twin simulations. You don't need a separate server for every function. You need one well-designed platform that handles multiple workloads. There are 3 deployment models that map directly to how enterprises are implementing this in 2026. In the virtual private model, the core functions share infrastructure with a mobile operator's enterprise core. Your traffic is logically isolated, but it exits through operator equipment. This is the fastest and cheapest way to deploy, but it offers the least dedicated control. It's a good fit for campus environments where cost is the primary driver and deterministic latency is less critical. In the hybrid model, signaling and control functions are shared or cloud-hosted, while the user plane is localized on-premises through a dedicated user plane function running on Azure Stack Edge. This model balances latency and data locality against complexity, and it's the pattern most mid-sized industrial sites are choosing in 2026. It gives you local breakout for sensitive traffic while still leveraging the operator's expertise for radio planning and spectrum management. In the standalone model, all core functions are dedicated and fully localized. This model provides the highest control and isolation, and it's the choice for mission-critical sites, defense-adjacent facilities, and heavily regulated environments where even shared infrastructure is unacceptable. The trade-off is higher cost and operational complexity because your team owns the entire stack. Deutsche Telekom's Campus Network Smart is a concrete example of the hybrid model in production. It uses Microsoft's Azure Private Multi-Access Edge Compute platform, including Azure Private 5G Core running on Azure Stack Edge, while Deutsche Telekom provides the radio access network components, spectrum, planning, and managed services. The service is billed as a pay-as-you-grow model, which reduces the upfront capital barrier that stops many edge projects before they start. You don't need to buy $1 million private network on day one. You start with a small deployment and expand as your use cases prove their value. Microsoft has also built explicit click-and-deploy integration for partner virtual network functions on Azure Stack Edge. Nokia Digital Automation Cloud can be deployed through Azure Network Function Manager, after which it connects to Nokia's cloud for SIM management and radio orchestration. Salona Edge deploys similarly, automatically calling home to the Salona orchestrator once it's running. Software-defined wide area network functions like VeloCloud can run on the same appliance, integrating your private 5G segment into your broader enterprise one. This ecosystem approach means you're not locked into a single vendor for every layer of the stack. For organizations already invested in Azure, the integration path is straightforward. Azure Stack Edge connects to Azure Arc, which means your on-premises Kubernetes clusters, your virtual machines, and your containerized applications are managed through the same Azure Resource Manager interfaces, the same policy definitions, and the same identity stack that governs your cloud workloads. The edge isn't an alien environment, it's an extension of the cloud that happens to live in your building. The hardware itself deserves a closer look because it's not a generic server. Azure Stack Edge Pro is designed for industrial and remote environments with features that standard data center servers lack. It has redundant power supplies, solid-state storage, and a form factor that fits into wiring closets or equipment rooms rather than requiring a dedicated data center. The GPU-enabled variants can run computer vision inference, digital twin simulations, and virtual network functions concurrently. Network acceleration features allow the appliance to handle packet core workloads without choking the CPU, which means the same box that routes your 5G traffic can also host your machine learning container without performance contention. The partner ecosystem around Azure Stack Edge is expanding rapidly. Nokia Digital Automation Cloud, Salona Edge, and several software-defined wide-area network virtual network functions are available through Azure Network Function Manager with click-and-deploy experiences. This ecosystem approach matters because it allows you to mix and match best-of-breed components without becoming a systems integration company. You select the validated virtual network function, approve the deployment, and Azure handles the lifecycle. The partner handles the specialized configuration. Your team focuses on the applications that create business value. Multi-access edge computing explained. Multi-access edge computing is the bridge between the 5G radio and the local compute power that makes real-time decisions possible. Without MEC, private 5G is just a very expensive wireless network. With MEC, it becomes an intelligent edge platform. In simple terms, MEC means placing compute, storage, and application hosting physically close to where data is generated and where actions must be taken. In Microsoft's ecosystem, this manifests through Azure Stack Edge devices running containerized workloads, Azure Arc-enabled Kubernetes clusters, and specialized network functions that process traffic before it ever touches the public internet. The typical architecture looks like this. Industrial sensors, cameras, robots, and autonomous vehicles connect to private 5G radios distributed across the facility. Those radios feed into the Azure private 5G core running on an Azure Stack Edge appliance. That same appliance hosts Kubernetes pods running computer vision models, predictive maintenance algorithms, digital twin simulations, or custom business logic. The data travels a few meters over a local network, gets processed in milliseconds, and only the results or exceptions are forwarded to Azure regions for long-term storage, model retraining, or cross-site analytics. Containerized logic is what makes this architecture agile. Instead of installing monolithic software on industrial personal computers that require manual patching and physical maintenance, you deploy containerized applications through Azure Arc. A new version of your defect detection model is trained in the cloud, validated in a staging environment, and rolled out to edge devices through a DevOps pipeline. The update happens without a technician walking the factory floor. The rollback happens automatically if the new model fails validation against live data. This is how cloud-native practices extend to the physical world. Azure IoT Edge provides the runtime for this containerized orchestration. It manages module deployment, monitors health, and handles offline operation gracefully. When connectivity is available, IoT Edge synchronizes telemetry, model updates, and configuration changes with Azure IoT Hub. When connectivity is lost, the edge devices continue running their last known good configuration. The facility doesn't stop because the internet hiccups. The local intelligence keeps working, and the cloud catches up when the link returns. The economics of MEC are also compelling when you look at the full stack. Manufacturers deploying MEC in 2024 through 2026 are seeing positive but highly use case dependent returns, with payback typically in 12 to 36 months when MEC is tied to clearly monetized outcomes. Predictive maintenance use cases often pay back in 3 to 6 months. Vision-based quality inspection typically pays back in 6 to 12 months. Energy optimization can pay back in 4 to 8 months. Digital twins, which are more complex, usually pay back in 12 to 18 months. The DevOps implications of MEC are just as important as the financial ones. In traditional industrial information technology, updating software on a factory floor meant scheduling downtime, sending a technician with a laptop, and manually copying files to industrial personal computers. The process was slow, error-prone, and expensive. Containerized edge computing changes this fundamentally. Your software development lifecycle now extends to the factory floor. A developer commits code to a repository in Azure DevOps. The continuous integration pipeline builds a container image. The continuous deployment pipeline pushes that image to Azure Container Registry. Azure IoT Edge pulls the updated module to the Edge device and rolls it out with zero downtime. If the new version fails a health check, the Edge runtime automatically rolls back to the previous version. This pattern is called Edge DevOps, and it's the reason why cloud-native companies can operate thousands of Edge locations with a small platform team. The Edge device becomes just another node in your Kubernetes cluster. The deployment manifest is just another YAML file in your Git repository. The monitoring dashboard is just another panel in your Azure Monitor workspace. The skills your team already has translate directly. Another practical aspect of MEC that enterprise architects often overlook is storage. Edge nodes don't just process data, they buffer it. When a wide area network outage severs the connection between your factory and Azure, the Edge node continues collecting sensor data, buffering it locally, and running analytics against the cached dataset. When connectivity returns, the node synchronizes the buffered telemetry in batches, compresses it, and forwards it upstream without overwhelming the restored link. This store and forward capability is built into Azure IoT Edge and is essential for environments with intermittent connectivity, such as offshore platforms, remote mines, and rural agricultural sites. These returns don't come from the MEC hardware alone. They come from what the MEC enables. The Edge node is the platform. The application is the value. Without a clear use case, MEC is just an expensive server in a closet. With a clear use case, it's the infrastructure that turns raw data into real-time action. The event reasoning orchestration model. Architecture diagrams are useful for planning, but they don't move production lines. So let me walk you through exactly how this works when a fault happens. Picture a high-speed automotive assembly line. A robotic arm is placing components onto a chassis, moving at a fixed speed. A vibration sensor on the arm detects an anomaly. The anomaly isn't catastrophic yet, but the pattern suggests a bearing failure within the next few hours. In a traditional cloud-first architecture, the sensor sends telemetry to a cloud region, the analytics engine processes it, an alert fires in a dashboard somewhere, and a maintenance engineer might see it within minutes or hours. By then, the arm may have already failed, stopping the line, scrapping in-process units, and requiring emergency repairs that cost 10 times more than planned maintenance. In the new model, the sequence looks completely different. The vibration sensor streams data over the private 5G network to an edge node sitting 50 feet away. The edge node runs a predictive maintenance container that processes the vibration signature in real time. The model recognizes the bearing failure signature and generates a health score. Because the edge node also hosts the manufacturing execution system connector, it can automatically reduce the arm's speed to a safe operating window, queue a maintenance work order, and notify the line supervisor through Microsoft Teams. All of this happens in under 10 milliseconds. The cloud doesn't even know it happened until the edge node uploads a summary log 10 seconds later. The cloud doesn't disappear in this scenario. The edge node uploads aggregated health trends, anonymized vibration signatures, and maintenance outcomes to Azure for model retraining. The cloud data scientist improves the algorithm using patterns from hundreds of similar sensors across multiple sites. The improved model is validated and pushed back to the edge through Azure IoT Edge. The local operation gets smarter over time, but the local operation never depends on the cloud to keep the line running. Let's look at another scenario. A computer vision system is inspecting weld quality on the same assembly line. A high-resolution camera captures every weld as the chassis passes. The image streams over private 5G to a GPU-enabled Azure Stack Edge appliance running a containerized vision model. The model evaluates the weld in under 100 milliseconds and flags a defect. A signal goes back over the 5G network to a reject station, which diverts the faulty chassis before it reaches the next assembly stage. Only the defect metadata, a thumbnail image, and the quality score are forwarded to the cloud for reporting and traceability. The raw video, which would have consumed massive bandwidth and incurred egress charges, never leaves the building. Now consider a healthcare scenario. A hospital deploys private 5G for real-time patient monitoring, mobile imaging cards, and connected surgical instruments. A patient's wearable cardiac monitor detects an arrhythmia. In the old model, the wearable buffers data and uploads it to the cloud every few minutes. In the new model, the wearable streams over a dedicated medical device slice of the private 5G network to an edge node in the hospital's equipment room. The edge node runs a validated cardiac analysis container that flags the arrhythmia in real time, triggers a nurse alert through the hospital's integrated communication system, and logs the event to the electronic health record through a secure on-premises gateway. The patient's protected health information never leaves the hospital's controlled environment, which satisfies both latency requirements and regulatory constraints. Finally, consider a port scenario. A container terminal spans several kilometers of quay, yard, and gate. Automated stacking cranes, automated guided vehicles, and ship-to-shore cranes must coordinate across a coverage area that Wi-Fi can't serve reliably. An automated guided vehicle carrying a 40-foot container approaches an intersection where another vehicle is already crossing. The vehicle's LiDAR and camera sensors detect the conflict. In the old model, this data might route to a cloud-based fleet management system, which calculates trajectories and sends commands back. The round trip takes too long. The vehicles stop and wait, creating a traffic jam that propagates through the yard. In the new model, the sensors stream over private 5G to an edge node located in the terminal operations center. The edge node runs a local fleet coordination container that processes all vehicle positions within the yard, calculates collision-free paths, and issues speed and steering commands in under 10 milliseconds. The vehicles never stop. The traffic flows. Only the aggregate throughput data, the exception reports, and the long-term utilization metrics travel to the cloud for terminal-wide optimization. In all 4 cases, the pattern is the same. The event happens at the source. The reasoning happens at the source. The orchestration happens at the source. The cloud provides governance, training, and long-term intelligence. But the milliseconds that matter are owned locally. If you attempted to run any of these loops through a cloud region, the round trip alone would consume 100 to 300 milliseconds, and that assumes ideal network conditions. Under congestion, peering delays, or regional load, the variability would make the control loop unstable. A robot that corrects its position based on 300 millisecond-old data isn't a precision instrument, it's a hazard. A cardiac monitor that waits 3 minutes to upload a critical event isn't a safety system, it's a liability. The architectural inversion is simple to state but difficult to internalize if your entire career has been built around centralized cloud architecture. The brain moves to the edge, the cloud becomes the nervous system, not the cerebrum. The edge handles reflexes, the cloud handles learning. Both are necessary, but their roles are reversed from what most cloud professionals assume. And here's the part that gets leadership's attention. This isn't just an engineering fix, it's one of the highest return infrastructure investments you can make right now. The real-world return. By now you're probably thinking this sounds expensive. It is, but the research shows it's also one of the highest return infrastructure investments an industrial organization can make in 2026. ABI research analyzed private 5G deployments across automotive manufacturing, electronics manufacturing, third-party logistics, and retail distribution warehousing. Their findings are striking. Operational cost savings from private 5G yielded an average return on investment of 28 times over a 5-year analysis period. That means savings far exceeded cumulative network costs by a factor of nearly 30. For a technology category that sounds like science fiction to many executives, that return is anchored in real operational metrics. For a Tier 1 United States factory, the same analysis estimated potential value of up to $1 billion over 5 years when private 5G is fully leveraged for automation, cloud-based quality control, and flexible production. Even an average factory can save hundreds of thousands of dollars per year on Ethernet cabling alone, because wireless connectivity replaces physical drops that each cost about $225 to install and maintain. When you add the labor savings from eliminating cable damage, the downtime reduction from faster line reconfigurations, and the flexibility to reconfigure layouts without rewiring, the infrastructure savings become a serious business case on their own. Cloud-based quality control enabled by 5G improved testing capacity by 25% in early deployments. That translates directly into higher throughput and lower per-unit cost. Higher inspection accuracy via edge-hosted vision models reduces defects and rework, which lowers scrap costs and improves yield. 5G-enabled autonomous guided vehicles allow dynamic routing and flexible production, which reduces idle time and supports smaller lot sizes with less changeover overhead. The factory becomes more responsive to demand without requiring new capital equipment. The predictive maintenance story is even more dramatic. Manufacturers deploying multi-access edge computing tied to predictive maintenance models are seeing payback periods of 3 to 6 months and 3-year returns of 400 to 500%. Rotating equipment outfitted with vibration and temperature sensors generates health scores locally, allowing maintenance teams to intervene before a failure stops the line. The average reduction in unplanned downtime on monitored assets runs between 20 and 50%. Maintenance labor and parts costs drop 10 to 40%. The savings aren't theoretical. They're measured in hours of recovered production time. Vision-based quality inspection typically pays back in 6 to 12 months with 3-year returns of 250 to 350%. Investment per line ranges from 80 to 200,000 euros for cameras, edge GPU servers, and software, but the scrap reduction in targeted defect categories often reaches 20 to 50%. First-pass yield improves 2 to 5 percentage points. Manual inspection labor drops 30 to 70%. The quality team stops sampling and starts inspecting every single part. Energy optimization via edge control pays back in 4 to 8 months with 3-year returns of 300 to 400%. Plants monitor HVAC, compressed air, ovens, and furnaces through sensors that feed local optimization algorithms, which adjust set points in real time based on production conditions. A 5 to 15% reduction in energy usage on targeted systems is common, and in high-consumption process industries, the absolute dollar savings are large. But the research also includes a sobering caveat that every executive should read twice. Brownfield plants, older facilities with legacy equipment and fragmented data infrastructure, typically need an additional 6 to 12 months of payback time compared with modern greenfield sites. The edge hardware isn't the bottleneck, the data foundation is. If your programmable logic controllers speak proprietary protocols, your historians use incompatible formats, and your manufacturing execution system was installed in the 1990s, the integration work will consume more time and budget than the 5G deployment itself. Another finding that should catch your attention. 42% of manufacturers have deployed artificial intelligence in some form, but only 12% operate at true multi-site enterprise scale. Most are stuck in pilot purgatory. They proved the technology works on one line. They generated a nice case study, but they haven't built the platform, the governance, or the organizational muscle to replicate it across the enterprise. The result is a portfolio of disconnected experiments that never compound into transformation. This is the pattern that separates companies that extract value from edge computing and companies that merely experiment with it. The winners treat Emeki as a shared platform that amortizes its cost across multiple use cases and multiple plants over a 3 to 5 year horizon. The marginal cost of adding the fourth or fifth application to an existing edge cluster is a fraction of the cost of the initial deployment. The losers treat each use case as a standalone project with its own infrastructure, its own vendor, and its own maintenance burden. They never achieve scale because they're too busy rebuilding the foundation for every new idea. Third-party logistics and warehousing present a specific ROI profile that differs from manufacturing. A large distribution center processing millions of packages per day can realize value from private 5G through automated sorting, robotic put-away, and real-time inventory tracking. The labor savings from automated guided vehicles and autonomous mobile robots often reach 20 to 40% of intralogistics labor costs. Reduced line stoppages due to missing material, which typically drop by over 30%, directly translate into faster order fulfillment and higher customer satisfaction scores. The payback period for warehouse automation via 5G and MEC typically runs 18 to 36 months, which is longer than predictive maintenance, but driven by labor cost arbitrage at scale. Energy and utilities offer another distinct ROI pattern. A wind farm with dozens of turbines spread across a rural landscape can't depend on fiber connectivity to each tower. Private 5G provides the backhaul for turbine condition monitoring, blade inspection drones, and substation protection systems. Edge nodes at each substation process protection relay data locally, ensuring that fault isolation happens in milliseconds even when the wide area network is down. The avoided outage cost, measured in dollars per minute of lost generation or distribution capacity, often dwarfs the network investment. A single prevented outage during a peak demand period can pay for the entire edge infrastructure. But money isn't the only wall you'll hit. Even the most profitable edge deployment collapses if your data ends up somewhere it shouldn't. Data sovereignty is not optional. A large distribution center processing millions of packages per day can realize value from private 5G through automated sorting, robotic put-away, and real-time inventory tracking. The labor savings from automated guided vehicles and autonomous mobile robots often reach 20 to 40% of intralogistics labor costs. Reduced line stoppages due to missing material, which typically drop by over 30%, directly translate into faster order fulfillment and higher customer satisfaction scores. The payback period for warehouse automation via 5G and MEC typically runs 18 to 36 months, which is longer than predictive maintenance, but driven by labor cost arbitrage at scale. Data sovereignty is not optional. None of this matters if your data ends up somewhere it shouldn't. And in 2026, that's not a hypothetical risk. It's a regulatory mandate with teeth. The European Union has created a compliance stack that reads like an alphabet soup, but carries the force of law across every industrial sector. GDPR still governs all processing of personal data at the edge, including collection, storage, profiling, and analytics. It requires visibility into what data is processed, where it resides, who can access it, and how it moves across borders. Data subject rights, including access, erasure, and portability, must be enforceable even when data is fragmented across edge nodes. If your edge deployment handles employee biometrics, patient telemetry, or visitor tracking, GDPR applies in full force. The Data Act, phasing in through 2026, focuses on data ownership, access, and portability for information generated by connected products and Internet of Things devices. It requires that users can access and port data their devices generate, preventing lock-in by proprietary edge platforms. For multi-tenant edge clusters, this means your platform must expose APIs and governance mechanisms that allow data extraction in structured formats. You can't bury user data in a closed container and call it secure. The AI Act reaches full enforcement in August 2026, introducing obligations for high-risk edge-based systems like computer vision, quality inspection, autonomous vehicle control, and predictive maintenance in safety-critical contexts. Edge-based artificial intelligence likely falls under high-risk categories, which means logs, training data governance, robustness testing, and documentation must be verifiable at the edge. You can't train a model in the cloud, deploy it to the edge, and pretend the edge has no compliance obligations. NIS2 applies to essential and important entities across energy, transport, health, digital infrastructure, and public administration. It requires robust cybersecurity measures, risk management, vulnerability handling, continuity planning, and incident reporting within 24 hours. Some member states demand 6 hours. If your private 5G core is the backbone of a hospital's telemetry network or a substation's protection system, NIS2 treats it as critical infrastructure. The edge node isn't a secondary system, it's a regulated system. DORA, the Digital Operational Resilience Act, primarily targets financial services, but sets a precedent that extends to any organization managing operational technology through third-party infrastructure. It imposes strict information and communication technology, risk management across the entire technology and third-party supply chain. You can't shift responsibility to your vendor or your open-source dependencies. You must perform regular risk assessments of every hardware supplier, software component, and managed service provider operating your edge stack. Post-Schrems 2, European regulators increasingly require technical and procedural proof of data handling, which means contractual promises alone are no longer enough. Standard contractual clauses are necessary but no longer sufficient on their own. Organizations are building playbooks for cross-border transfer events and government access requests. Edge platforms must log and, where possible, prevent unexpected data egress to third countries. The architecture must enforce residency, not just assert it in the contract. 44% of European organizations doubt that hyperscale cloud providers can genuinely guarantee data sovereignty. That's not a fringe opinion. That's nearly half the market expressing a trust gap. In response, many organizations are turning to self-hosted systems and private edge for high-sensitivity workloads to ensure full control over data, infrastructure, and access paths under European law. The practical prioritization emerging in 2026 places high priority on self-hosting customer databases, internal communications, document storage, analytics with user data, and identity management. Public marketing sites and generic tools without sensitive data remain lower priority. 51% of organizations see enhanced customer trust as a benefit of strong sovereignty, and 33% see it as a competitive advantage. This is a market signal that compliance is becoming a differentiator. Customers, partners, and regulators are increasingly asking for proof of data handling rather than verbal assurances. The organizations that can demonstrate verifiable sovereignty through their architecture will win contracts in defense, healthcare, energy, and finance. The organizations that rely on contractual clauses alone will find themselves excluded from procurement processes that require technical evidence. The shift is from contract-first compliance to architecture-first compliance. Contracts can't override foreign laws. Only architecture can reliably prevent or limit cross-border access. In-jurisdiction encryption, key custody, infrastructure-level access controls, geofencing of workloads, and exportable audit trails are becoming baseline requirements, not advanced features. Your Chief Information Security Officer doesn't need another policy document. Your edge platform needs technical controls that prove compliance without human interpretation. By 2030, the European Union aims for 10,000 climate-neutral and highly secure edge nodes deployed across the continent, tightly connected to cloud infrastructure and common data spaces. The proposed Cloud and Artificial Intelligence Development Act, introduced in June 2026, targets tripling European data center capacity within 5 to 7 years with an explicit focus on digital sovereignty. The message from regulators is unambiguous. Where data lives matters. Architecture is the only trustworthy answer. Security at the edge. Regulations tell you where data must stay. Security tells you who can touch it. And private 5G introduces a security model that's fundamentally different from traditional enterprise wireless. The difference starts at the identity layer. Wi-Fi relies on shared passwords and certificates that can be copied, leaked, or socially engineered. An employee writes a password on a whiteboard. A contractor shares a certificate over email. A device joins the wrong network because the network names look similar. These are not exotic attack scenarios. They are daily occurrences in enterprise environments. Private 5G relies on subscriber identity modules or embedded subscriber identity modules for hardware-anchored identity. Each device has a unique cryptographic identity that the network authenticates individually. You can't shoulder surf a 16-digit cryptographic key. You can't guess a SIM, and you can revoke a compromised device instantly without rotating a shared credential that affects every other device on the network. When an employee leaves, you don't change the factory Wi-Fi password and reconfigure 500 devices. You deprovision one SIM record in the Azure portal. Zero Trust architecture maps naturally onto private 5G. Mutual authentication between device and network is built into the protocol, not bolted on afterward. On the core side, mutual transport layer security between service-based interfaces, microsegmentation of slices, and continuous authorization based on device posture are all native capabilities. Network slicing enables logical separation of traffic, which means mission-critical clinical or operational traffic can be isolated from guest or administrative traffic at the radio level instead of only at the firewall. A compromised guest laptop can't jump to the robot control slice because the slices are enforced by the base station scheduler. Industrial cybersecurity standards are also catching up to the private 5G world. IEC 62443, the established framework for industrial control system security, now maps directly to private 5G components. The 5G core functions are treated as control system components within specific security zones. Subscriber identity modules, base stations, and Internet of Things gateways are classified as endpoints with defined security levels. This alignment is critical because it allows healthcare, energy, and manufacturing organizations to adopt private 5G without inventing a new security vocabulary or hiring a separate audit team. Microsoft's Azure Private 5G Core integrates into the security tooling that most Azure customers already operate. Azure Monitor collects metrics and logs. Microsoft Defender for Cloud assesses security posture. Microsoft Entra ID governs administrative access. Azure Policy enforces configuration baselines. The private 5G Core doesn't sit outside your security ecosystem. It becomes another managed resource within it. Your Security Operations Center doesn't need a separate screen for the factory network. It sees the factory network in the same dashboard as the cloud tenant. But a word of caution is necessary. Private 5G isn't automatically secure just because it uses cellular protocols. Trend Micro's analysis of private 5G deployments found that many lack mature multi-layered security, including next-generation firewalls, intrusion detection and prevention, and continuous monitoring. Misconfigurations, unpatched components, and insecure integration with existing information technology and operational technology systems create risks that the radio layer can't fix. The 5G core and its management interfaces become high-value targets precisely because they control so much critical infrastructure. Integrating the core into your identity stack, your security operations center, and your incident response framework isn't optional. It's the difference between a secure edge and an expensive vulnerability. You need intrusion detection that understands 5G control plane and user plane traffic. You need behavioral analytics that flags unusual device behavior, like an infusion pump scanning network ports it shouldn't touch. You need incident response plans that cover compromised SIMs, rogue base stations, and misconfigured slices. And you need regular red teaming and tabletop exercises that include 5G-specific scenarios. The supply chain is another attack surface that many organizations underestimate. You must treat 5G core software and radio firmware as critical assets, maintain software bills of materials, apply security patches promptly, and use secure update channels. Assess suppliers for secure development practices and compliance certifications. If your edge hardware vendor has a vulnerability in their baseband processor, your entire private network is exposed regardless of how strong your SIM-based authentication is. One specific threat vector deserves mention because it's counterintuitive. Rogue base stations, sometimes called IMSI catchers or stingrays in the public cellular world, are devices that impersonate legitimate base stations to intercept traffic or force devices to downgrade to insecure protocols. In a private 5G network, this threat is reduced because the network uses mutual authentication. The device verifies the network's identity in both directions, but misconfiguration can disable this protection. If your deployment team skips certificate validation to solve a connectivity issue, they may have just opened a window for an attacker to park a rogue G-Node B in your parking lot and capture operational traffic. The technical safeguard exists. It must be enabled, tested, and monitored. Another emerging threat is artificial intelligence model poisoning at the edge. If an attacker gains access to your edge container registry or your model update pipeline, they can inject a subtly corrupted model that produces false negatives on defect detection or false positives on predictive maintenance alerts. The corrupted model might not be obviously wrong. It might just be slightly less accurate, causing your maintenance team to lose trust in the system over time. Securing the model supply chain, validating model integrity with cryptographic signatures, and monitoring model behavior for drift are essential practices that most organizations haven't implemented yet. The converged fabric. You won't replace your Wi-Fi overnight. The smart move is a converged fabric that uses each technology where it wins. Wi-Fi 7 is the default choice for indoor enterprise connectivity in 2026. By the third quarter of 2025, Wi-Fi 7 already accounted for 31.1% of enterprise access point revenues, and North American spending is shifting strongly toward the new standard. Wi-Fi 7 offers very high throughput, multi-link operation for reduced congestion and improved efficiency for collaboration, video conferencing, and general office workloads. The Wireless Broadband Alliance trials showed that Wi-Fi 7 delivers nearly double the throughput of Wi-Fi 6E in certain configurations and sustains over 1 gigabit per second at 40 feet from the access point using 6 GHz spectrum with 160 MHz channels. For knowledge work, Wi-Fi 7 is the right tool. It doesn't merely suffice, it excels. It supports the laptops, tablets, phones, and augmented reality headsets that your office workers rely on. Multi-link operation is the headline feature that distinguishes Wi-Fi 7 from its predecessor. It allows a device to transmit and receive across multiple frequency bands simultaneously, which reduces latency by avoiding congested channels rather than waiting for them to clear. In a clean indoor environment with few competing networks, Wi-Fi 7 can achieve one-way latencies in the 1 to 5 millisecond range under light load. But under moderate to heavy load, with many clients contending for airtime and neighboring access points causing interference, tail latency can spike to tens of milliseconds. For video conferencing and file transfers, those spikes are invisible. For robotic control, they're unacceptable. Private 5G anchors the operational technology layer where determinism, mobility, and guaranteed quality of service are non-negotiable. In large outdoor sites like ports, mines, airports, and energy facilities, Wi-Fi coverage and interference management become challenging, and device mobility is critical. Private 5G handles these scenarios with engineered handover behavior and predictable latency under load. The base station scheduler guarantees that a safety command gets through even when the network is carrying video, telemetry, and voice simultaneously. The converged model is already dominant in enterprise planning. Around 60% of businesses see converged Wi-Fi and 5G as key to enterprise flexibility, viewing them as complementary rather than competitive. Device and customer premises equipment vendors are integrating both technologies into single platforms to ensure consistent user experience. The long-term vision is a single logical fabric where applications express requirements like latency, reliability, and bandwidth, and the network orchestrator decides whether traffic uses a Wi-Fi slice or a private 5G slice based on policy. This isn't science fiction. It's the architecture that Deutsche Telekom, Cisco, and several industrial integrators are deploying in 2026. Azure Arc is the management layer that makes this convergence practical. It extends Azure's management, policy, identity, and Kubernetes orchestration to both Wi-Fi connected and 5G connected edge devices, as well as back to Azure regions. Your Azure Stack Edge appliances, your Arc-enabled Kubernetes clusters, your on-premises virtual machines, and your cloud virtual machines all appear in the same Azure portal. The same resource groups, the same role-based access control, the same tagging policies, and the same DevOps pipelines govern the entire continuum. This matters because it prevents the edge from becoming a management silo. In too many organizations, the operational technology team manages the factory network, the information technology team manages the corporate network, and neither talks to the cloud team. Azure Arc breaks down those walls by providing a unified control plane. The edge becomes part of the cloud estate, not an exception to it. Your cloud architect can define a Kubernetes policy that applies to clusters in Azure East US, Azure West Europe, and your factory floor simultaneously. Your security engineer can enforce a network rule that spans cloud virtual machines and edge appliances without learning a new tool. The edge-to-cloud continuum isn't a binary choice, and treating it as one leads to the same centralization fallacy that created the latency wall in the first place. At one extreme, embedded microcontrollers handle microsecond-level control loops directly attached to sensors and actuators. These devices will never run Kubernetes or connect to Azure Arc. They exist in a world of real-time operating systems and bare metal programming. At the other extreme, global analytics platforms and artificial intelligence training systems operate in hyperscale data centers on historical data. Between those extremes lie many layers. Industrial personal computers handle millisecond tasks. Facility local edge clusters host sub-100 millisecond analytics. Metro multi-access edge computing sites serve campus-level workloads. Regional data centers handle aggregation. And the global cloud handles model training, cross-site benchmarking, and governance. The convergence of Wi-Fi 7 and private 5G also creates interesting opportunities for device manufacturers. In 2026, several industrial device vendors are shipping dual radio modules that can associate with both Wi-Fi 7 and private 5G simultaneously. A ruggedized tablet carried by a maintenance technician might use Wi-Fi 7 for high-bandwidth document downloads while in the break room, then seamlessly transition to private 5G for low-latency augmented reality guidance when the technician walks onto the production floor. The device doesn't force the user to choose a network. The policy engine selects the optimal path based on application requirements, signal strength, and cost. This is the converged fabric in action. It's not two separate networks that users must navigate. It's one logical network that adapts to context. The art of architecting an edge-aware solution lies in decomposing applications so that each component runs at the layer where it best balances performance, cost, manageability, and compliance. Azure's platform is explicitly designed to span this continuum, from Azure real-time operating systems and embedded software development kits through Azure Stack Edge devices and Arc-enabled Kubernetes clusters to Azure regions and global software as a service like Microsoft 365. You don't need to abandon the tools you know, you need to apply them at the right layer. Deployment patterns that work. Knowing what to build is one thing. Knowing how to roll it out without bankrupting the project is another. The research on multi-access edge computing and private 5G deployments reveals a clear pattern. Organizations that succeed follow a phased approach. Organizations that fail try to transform everything at once. Phase 1 is data foundation and pilots, lasting roughly 0 to 6 months. The goal isn't to deploy a factory-wide edge platform on day one. The goal is to establish connectivity for a small set of sensors or cameras, deploy a minimal edge footprint, and choose 2 to 3 high-return use cases with existing baselines. Predictive maintenance on a single critical asset line is a common starting point because the baseline is easy to measure and the return is fast. Vision-based quality inspection on one production cell is another good starter because the scrap cost is visible and the improvement is quantifiable. These pilots generate operational data, prove the technology works in your environment, and create the financial evidence you need to justify scaling. During phase 1, you also establish your data foundation. This is the least glamorous part of the project and the most important. You catalog your sensors, you standardize your telemetry formats, you build the integration points between your edge nodes and your existing manufacturing execution system, supervisory control and data acquisition system, or enterprise resource planning system. If your factory runs on proprietary protocols from the 1990s, this integration work will take longer than the 5G deployment itself. Don't skip it. Don't outsource it to a vendor who doesn't understand your specific line. Your operations team must own this foundation because they're the ones who will live with it for the next decade. Phase 2 is validation and scaling planning lasting 6 to 12 months. Collect 3 to 6 months of operational data and quantify savings. Document unplanned downtime reductions, scrap rate improvements, energy savings, and labor efficiencies. Compare the pilot performance against the baseline you established in phase 1. Build a financial model that allocates edge platform costs across multiple use cases and multiple plants. The key output of phase 2 isn't more technology. It's a playbook that your operations team trusts and your finance team approves. Phase 3 is scaled deployment lasting 12 to 24 months. Expand edge clusters and use case coverage across multiple lines and sites. Add more advanced workloads like digital twins, autonomous scheduling, or supply chain optimization. The marginal cost of adding a new application to an existing edge platform is much lower than the cost of the initial deployment, which means your return on investment accelerates as you scale. A plant that started with predictive maintenance on one line might add vision inspection on 3 lines, energy optimization on the HVAC system, and a digital twin for line balancing. All 4 use cases run on the same Azure Stack Edge appliances and the same private 5G radios. Phase 4 is operationalization, lasting 24 to 36 months. Integrate edge applications with manufacturing execution systems, enterprise resource planning workflows, and cloud analytics. Build an internal center of excellence to manage multi-access edge computing and artificial intelligence operations. Train your maintenance technicians to interpret edge-generated health scores. Train your quality engineers to adjust vision models. Train your IT team to manage Arc-enabled Kubernetes clusters on the factory floor. The goal is to move from project mode to operational mode, where edge intelligence is just how the factory runs. 2 main perspectives compete for mind share in 2026. The use case first approach starts from concrete, high return objectives and justifies the edge platform as the cheapest, most reliable way to deliver them. This is the dominant pattern and the one that produces the fastest financial validation. It works because each use case has a clear owner, a clear baseline, and a clear payback formula. The platform-first approach treats the edge as shared plant-wide infrastructure, similar to a manufacturing execution system or supervisory control and data acquisition system, and amortizes its cost across a portfolio of applications over 3 to 5 years. This pattern is more common in large enterprises building standardized architectures across multiple plants. Both approaches work, but both have pitfalls. Underestimating integration complexity is the most common failure mode. Connecting edge nodes to legacy, programmable logic controllers, proprietary protocols, and multiple enterprise resource planning systems takes longer than the vendor demo suggests. Pilot purgatory is the second most common trap. A pilot shows technical success but lacks rigorous financial validation, which makes it impossible to secure funding for scaling. The third trap is lack of cross-functional ownership. Projects run solely by information technology or engineering without operations buy and struggle to scale because the people who must use the system weren't involved in designing it. If the maintenance team doesn't trust the predictive model, they won't act on its alerts. If the quality team doesn't understand the vision system, they'll override its decisions. The most important prerequisite for strong return on investment isn't the hardware, it's data quality and contextualization. Clean, tagged, standardized data is the foundation that makes artificial intelligence and edge analytics valuable. A $1 million GPU cluster running on dirty data produces $1 million noise. Before you buy the edge appliance, audit your data. Fix your historians, standardize your tags, map your data flows. The edge platform will amplify whatever data culture already exists. If your culture is disciplined, the edge will make you faster. If your culture is messy, the edge will make your mess real time. Vendor selection is another critical decision that shapes your trajectory. The multi-vendor ecosystem around Azure Private Multi-Access Edge Compute offers flexibility but also integration risk. From analysis, Mason noted that integration challenges across multi-vendor equipment continue to stifle growth, with system integrators facing genuine difficulties, making equipment from different vendors interoperate seamlessly. Microsoft's response has been to build a robust partner network and provide pre-validated solutions through Azure Network Function Manager. But pre-validated doesn't mean plug and play. You still need skilled integrators who understand both the radio layer and the Azure layer. The organizations that shortcut this step by hiring the cheapest contractor often spend twice as much fixing the integration 6 months later. Another practical consideration is the staffing model for ongoing operations. A private 5G edge deployment isn't a set-it-and-forget-it infrastructure. The radio environment changes as machines move, walls are erected, and new equipment introduces interference. The artificial intelligence models drift as product mixes change. Seasonal lighting shifts and sensor calibrations degrade. The containers require patching, the Kubernetes clusters require upgrades, and the security certificates require renewal. Someone needs to own this operational workload. In successful deployments, this is a dedicated platform team of 3 to 5 people who split their time between edge operations, model validation, and integration support. In unsuccessful deployments, this work is added to an already overloaded network engineer's desk, and the system gradually falls into disrepair. Return on investment calculations should also include the cost of organizational change. Training programs, cross-functional workshops, pilot site visits, and external consulting for change management are real costs that belong in the business case. Too many edge projects present a technical return on investment that ignores the human cost of adoption. The maintenance technician who has spent 20 years listening to bearings with a stethoscope won't trust a vibration algorithm until someone explains how it works, shows its track record, and involves them in tuning the thresholds. The line supervisor, who has always relied on visual inspection, won't delegate quality control to a camera until they see the camera catch defects they missed. These transitions take months, not weeks, and they require patience that aggressive project timelines rarely accommodate. Change management is the hidden multiplier that separates successful deployments from expensive failures. Your maintenance technicians need training to interpret edge-generated health scores instead of relying on manual vibration checks. Your quality engineers need training to adjust vision model thresholds when the product mix changes. Your IT team needs training to manage Arc-enabled Kubernetes clusters, troubleshoot container failures, and update baseband firmware. And your operational technology team needs training to trust the system enough to act on its alerts. A predictive maintenance alert that the maintenance team ignores because they don't trust the algorithm isn't a return on investment. It's a sunk cost. The organizational structure also matters. The most successful edge deployments in 2026 establish a cross-functional edge center of excellence that includes representatives from IT, OT, engineering, quality, safety, and finance. This team owns the platform roadmap, governs use case prioritization, and manages vendor relationships. It meets weekly during pilots, monthly during scaling, and quarterly during operationalization. Without this dedicated team, edge projects drift between departments, lose executive sponsorship, and stall when the initial champions move to new roles. What this means for your cloud strategy. The hardest part of this transition isn't the hardware or the software. It's the gap between the people who run your network and the people who run your factory. Information technology and operational technology teams speak different languages. Cloud teams prioritize agility, scalability, and rapid iteration. They accept that systems may occasionally be unavailable for maintenance or updates. They celebrate weekly releases and continuous deployment. Factory teams prioritize availability, predictability, and safety. They know that a machine that stops unexpectedly can cause financial loss or physical damage. Technology cycles in operational technology are longer. Machines may operate for decades. Changes must be carefully validated. A bad software update in the cloud causes a brief outage. A bad software update on a safety system causes an injury. When cloud-oriented teams attempt to extend information technology architectures directly into operational technology environments without accounting for these differences, they encounter resistance, and the solutions they propose fail under real-world conditions. The latency wall is a network problem, but it's also a cultural wall, a governance wall, and a skills wall. Private 5G, multi-access edge computing, and sovereign edge patterns represent a way to bridge this gap using cloud-aligned technologies that operational technology teams can accept. They allow information technology teams to bring modern DevOps practices, artificial intelligence, and analytics into industrial contexts while maintaining the determinism, isolation, and resilience that operational technology demands. But achieving this requires careful design of latency budgets, safety boundaries, and fallback modes so that cloud dependencies never compromise core industrial operations. Your governance model must change. Latency budgets become architecture requirements, not network optimization targets. Data residency becomes a design constraint, not a policy afterthought. Security zones follow IEC 62443 mappings instead of only corporate firewall rules. Change management for edge applications must include operational technology sign-off, not just information technology approval, and the edge stops being an exception to your cloud strategy and starts being an extension of it. This means your cloud center of excellence must learn operational technology concepts. Your network architects must understand control loops. Your data scientists must learn that a model that scores 95% accuracy in the lab might fail on the factory floor because the lighting changed or the sensor drifted. Your DevOps engineers must accept that some updates can't happen during the day shift. And your operational technology teams must learn that containers, Kubernetes, and infrastructure as code are not threats to stability. They're tools for delivering stability at scale. Latency budgets should be written into your architecture review process the same way you review cost estimates and availability targets. Every edge application should have a documented latency requirement, a measured baseline, and a validation test that runs after every deployment. If a new container version increases inference time from 50 milliseconds to 200 milliseconds, the deployment should fail automatically. This isn't an information technology policy, it's a safety policy. Data residency requirements should be modeled as data flow diagrams rather than only legal checklists. Your compliance team should be able to trace every byte from sensor to edge to cloud and demonstrate that raw operational data never crosses a jurisdictional boundary without explicit approval. This requires metadata tagging at the point of ingestion, geofencing policies in your container orchestrator, and audit logs that prove enforcement. The architecture must prevent violations by design, not detect them after the fact. The convergence of information technology and operational technology also changes your hiring and staffing models. You need people who speak both languages. The ideal edge architect in 2026 understands Azure Kubernetes Service, programmable logic controllers, and network quality of service. They can write a Helm chart and read a ladder logic diagram. They can explain network slicing to a plant manager and explain safety interlocks to a cloud engineer. These hybrid professionals are scarce and expensive, which is why the organizations that invest in training their existing staff rather than hiring unicorn candidates are winning the talent war. The good news is that the tools you already use extend naturally. Azure Arc manages Kubernetes clusters on the factory floor with the same policies that govern your cloud subscriptions. Microsoft Entra ID governs access to edge management interfaces. Microsoft Defender for Cloud assesses the security posture of your Azure Stack Edge appliances. Power Apps can interface with Edge application programming interfaces to display real-time occupancy or asset locations. Power Automate can trigger workflows based on events detected by Edge Analytics. Power BI can visualize both local metrics and aggregated cross-site metrics. The Edge isn't an alien world, it's Azure, moved closer to where the work happens. But the skills gap is real. Most Microsoft 365 administrators have never configured a 5G network slice. Most Power Platform developers have never deployed a container to an Edge Kubernetes cluster. Most Azure architects have never negotiated with a factory safety officer. These gaps close through training, through pilot projects that pair information technology and operational technology staff, and through centers of excellence that document patterns and share them across sites. The shift from navigation to context. If you've been listening to this channel for a while, you'll recognize the deeper pattern. Work doesn't start with navigation anymore. It starts with context. Your intranet failed because it was designed for structure, not for how people actually find answers. Pages, hierarchies, the assumption that people know what they're looking for. That assumption is broken because today, work doesn't start with navigation. It starts with context. Your Azure landing zone slows you down because it was designed for control, not for speed. Standardization at the wrong layer creates friction, not scale. The governance model that enables 100 developers in a software company might strangle a factory team that needs to move fast. And your cloud strategy fails at the edge because it was designed for centralization, not for local decision-making. It assumes that intelligence lives in the cloud, and the edge is just a dumb terminal. That assumption is broken. The latency wall exists because we tried to navigate every decision back to a central brain. We assumed that the right place for compute is wherever the data center is largest. We optimized for consolidation when we should have optimized for proximity. We treated the edge as a consumer of central services when it needed to be a producer of local intelligence. In the new model, context lives at the edge. Data, compute, and decisions live where the work happens. The cloud doesn't disappear. It shifts from being the starting point to being the supporting layer. It trains models, it governs policies, it connects sites, it provides the long-term intelligence that no single edge node could generate alone. But the reflexes, the real-time responses, the safety-critical decisions all happen locally. For Microsoft 365 and Power Platform professionals, this shift is an opportunity, not a threat. The same skills you use to build cloud applications, manage identities, and secure data estates now extend to the edge. The same low-code tools can orchestrate physical workflows. The same governance frameworks can span from the factory floor to the global tenant. You don't need to become a radio engineer. You need to understand that the edge is now part of your estate. and your estate is no longer defined by geography. Consider a practical example that bridges the Microsoft 365 world and the industrial edge. A quality manager uses Power BI to monitor first-pass yield across 6 factories. In the old model, the dashboard refreshes every hour from a cloud data warehouse that receives batch uploads from each site. By the time the manager sees a yield drop at Factory 3, 2,000 defective units have already shipped. In the new model, the edge node at Factory 3 streams real-time yield data to a local Power BI report that refreshes every minute. When yield drops below threshold, Power Automate triggers a maintenance alert to the line supervisor's Teams channel, creates a corrective action ticket in the local enterprise resource planning system, and logs the exception for the quality manager's consolidated dashboard. The quality manager still sees the global view, but the local action happens before the defect becomes a shipment. This pattern applies across the Microsoft stack. Microsoft Teams becomes the alert layer for edge-detected anomalies. SharePoint becomes the document repository for edge-generated compliance logs. Power Apps becomes the interface through which floor supervisors interact with edge-hosted digital twins. Lists and Loop become the coordination tools for cross-site edge rollouts. The edge doesn't replace Microsoft 365, it extends it into spaces where milliseconds matter. The journey from the old model to the new model isn't a single project, it's a capability that compounds over time. The first edge node you deploy will feel awkward. Your team will struggle with the new tooling. Your operational technology colleagues will be skeptical. Your finance team will question the capital expenditure. But the second deployment is easier. The third is routine. By the fifth, your edge platform is just infrastructure, and your teams are focused on applications that create value rather than cables that carry bits. Your cloud strategy wasn't fundamentally wrong. It was just built for a world where milliseconds didn't matter. Now they do. The organizations that win the next decade won't be the ones with the biggest cloud footprint. They'll be the ones that learn to place intelligence where the work actually happens. The latency wall isn't a ceiling, it's a door. Walk through it and you stop managing infrastructure from a distance and start orchestrating outcomes where they actually matter. If this changed how you think about architecture, follow Mirko Peters on LinkedIn and subscribe to the M365 FM podcast for more deep dives that connect the dots you didn't know were connected.